Hello, in today's video we are going to go over intermolecular forces. So, intermolecular forces are going to be electrostatic forces or attractions between molecules. Not to be confused with intramolecular forces. So, intramolecular forces are basically our bonds. So these are going to be the force that binds atoms together in molecules or compounds. With a intermolecular force, I-N-T-E-R, we can also have it between parts of molecules if the molecules are large enough. Okay? So we're going to be looking at that. We can kind of think about it as the glue that holds molecules together, where the glue between gas molecules is very weak, the glue that holds liquid molecules is a little bit stronger, glue that holds solid molecules or particles together is much stronger. So the stronger the glue, the more tightly things are held together. So the stronger the intermolecular force, the stronger things are held together. So we base intermolecular forces on electrostatic potential energy. So I'm going to use IMFs as intermolecular forces, just to make things easier and quicker. Okay, so strength based on the strength of those intermolecular forces are based on electrostatic potential energy. So what we talked about in the last video. So remember that our electrostatic potential energy, that force, that potential energy, is going to be directly proportional to the charge of your particles divided by their distance. So the larger the magnitude of those charges, the smaller the distance, the greater that electrostatic potential energy, and therefore the greater the intermolecular forces. So greater magnitude of Q1 and Q2, smaller distance between the charges, greater electrostatic potential energy, and therefore greater intermolecular forces. Okay, I've just shown this diagram to kind of show the difference between intramolecular forces and intermolecular forces. So an intramolecular force would be covalent bonds and ionic bonds, and they're significantly stronger than our intermolecular forces. So intra holds our atoms together, inter holds our molecules together. So it's going to be the force between basically charged particles. Well, partially charged particles. Okay? And it is going to be much weaker than our intramolecular forces. Okay, we're going to look at three types of intermolecular forces in pure substances. So for a pure substance, so not a mixture, we have three types of intermolecular forces. These include dispersion forces, dipole-dipole forces, and hydrogen bonding. And we're going to go into each of these. These right here are called van der Waals forces as well. So you may hear that term. Okay, and we're going to start with dispersion forces. Dispersion forces themselves, also called London dispersion forces, are going to be seen in every collection of atoms or molecules. So we would say that every substance exhibits dispersion forces. Or every covalent substance. Same thing with a collection of molecules. Okay, so when we think about dispersion forces, we're basically thinking about a asymmetric electron distribution. So we can take anything that has electrons, and remember that our electrons around our atom are not set in place. So electrons around an atom they're not stationary. Or set. We generally think about an atom having an average distribution, right? So if we have a non-polar substance or atom, an individual atom, then the average distribution of that electron density will result in no dipole. Okay, so we can take xenon, for instance. Xenon, a xenon gas is composed of a bunch of xenon molecules, or sorry, xenon atoms, and they have 54 electrons, right? So each xenon atom has 54 electrons. In general, its electron distribution will look kind of spherical-esque, right? Let's put that as a plus. So we've got our nucleus in the center and our electron distribution on the outside, and the electrons are going to be evenly distributed around that positive charge. Okay? Now, let's say we come in contact with another xenon. So I'm just going to take duplicate. Voila. So now I have two xenon molecules, or xenon atoms. And when they come in contact, the electrons are going to repel one another. So we're going to get some repulsion. Of the electron clouds. And what we're going to get is a shifting for a moment of that electron density. for an instant, if you will. By the presence of this other one. Okay? And then we have what we call an instantaneous dipole. Okay? And eventually, and we could write it like this, draw it like this, where we have an unsymmetric or asymmetric distribution of that electron density, and we have a partial positive area and a partial negative area. That asymmetric distribution of that xenon molecule will affect other xenon molecules around it, and eventually will result in a bunch of instantaneous or induced dipoles. So this right here would be an induced dipole. It only lasts for an instant. It's not a permanent thing, it's not a permanent dipole, but because we get an instantaneous or induced dipole that can induce other dipoles, we get some electrostatic interactions going on. We would call this shift in electron density, or ability to shift or distort the electron density, polarizability. So a molecule's polarizability, molecule or atom's polarizability, is its ability to distort its electron cloud or distort its charge distribution. So we kind of think about something that is highly polarizable, something that can very easily distort its charge distribution. So something is polarizable, we call it squishy. So we can push that electron density in one direction or another. Okay? And some things that are going to affect our polarizability and our ability to induce a dipole is going to be the number of electrons. More electrons, the more easy we are, or the easier it is to distort those electrons in one direction or another, and also kind of the distance the electrons are from the nucleus. So here we're thinking our effective nuclear charge, or Z effective. So remember, if we have a large Z effective, our nucleus is going to pull electron density towards itself, and we wouldn't think of that to be something very squishy. That's something much more hard. So it's harder to push electron density in one direction or another. So we want something where our electrons aren't really held tightly to the nucleus, but we also want to have a lot of electrons, and that'll result in something that is more polarizable. Okay? So, this being said, we're going to increase polarizability by increasing our molecular weight and increasing our surface area. MW is molecular weight. And then by increasing our surface area. So, let's take, for instance, these two molecules right here. These are both C8, H18. So they both have the same molecular weight. The one on the left is going to be more polarizable. And it's because it has a greater surface area, so it can push electron density in one direction more greatly than the one on the right, which is less polarizable. Okay, if we think about this in kind of like as a charge distribution, let me go with these colors. So with this one, if we were to bring in a negative charge here, we can induce a dipole, push this electron density to the right, and since we have such a long molecule, we can get a very large partial negative and partial positive by just changing. So let's put this out here by just pushing our electron density to one side of this molecule. On the right one, if we come in contact with a negative charge again, we can't push that electron density quite as far because our molecule is not as large. So it's still going to stay around the atoms, right? They're tethered to the atoms. They're just, they can only push so far away from that atom. So even though we still have a negative charge interacting with the same number of electrons, they're not able to push as far away from that negative charge, so that partial charge is not going to be as great. Okay, we can also see that the polarizability effect, if we take different size molecules that have the same kind of shape, the more electrons, the more atoms, the more polarizable. So this one on the left is going to be the most polarizable, and this one down here is going to be the least, and that is just based on size, number of atoms. So as we increase our number of atoms, we're going to increase our polarizability. And remember that the more polarizable, the greater the dispersion forces. So because we can get a larger charge, we have a larger Q value, so the intermolecular forces between more polarizable molecules will be greater than the intermolecular forces between less polarizable molecules. And those intermolecular forces, the greater those forces, the more those molecules are held together. So that's going to affect a lot of different properties, which we're going to look at in the next video. Okay, we're going to look at two other intermolecular forces. We're going to look at dipole-dipole first. So again, dispersion forces, those are seen in all molecules, and they're affected by molecular weight and our surface area. Dipole-dipole forces are not affected by molecular weight, and this is going to be an intermolecular force between two molecules with permanent dipoles. So when we looked at polar molecules have dipole-dipole interactions. Okay, so because, real quick, our dispersion forces are going to be a weak force. So dispersion force so it's going to be somewhere between 1 and or 0.1 and 30 kilojoules per mole in energy, right? So we can look at the energy of these interactions. Our dipole-dipole is going to be a stronger force because instead of having dipoles, we have permanent dipoles. So they're going to be stronger. Our Q value of our electrostatic force equation is going to be stronger. So we have an electrostatic interaction between the positive pole of one polar molecule and the negative pole of another polar molecule, or if we have a large enough molecule, it can be of the positive pole of one side, negative pole of another side. So that's our electrostatic force between the positive pole of one molecule and the negative pole of another molecule. So we have to have permanent dipoles. So any polar molecule will exhibit this. Okay, this will be a medium strength interaction. Between 2 and 15 kilojoules per mole. Okay, so there are some dispersion forces that can actually be stronger than dipole-dipole, but generally dipole-dipole is going to be stronger than our dispersion forces. So technically this is a weak to medium here. And then this is just going to be a medium force. So here is an example of some dipole-dipole interactions. Hydrochloric acid. Hydrogen has a electronegativity 2.0, and then our electronegativity of chlorine is 3.5. So our difference in electronegativity is 1.5, so we know that's a polar bond. So we'll have a partial positive and a partial negative. That partial negative chlorine will interact with the partial positive hydrogen on a different molecule, and this right here, as is shown here, is going to be our dipole-dipole attraction. Okay, so anything that has a permanent dipole can do a dipole-dipole interaction. Okay, last one we want to look at is hydrogen bonding. And this is going to be our strongest within our pure substances, and is the attraction between a hydrogen atom attached to a highly electronegative atom so we're talking nitrogen, oxygen, or fluorine, and a nearby small electronegative atom so again, nitrogen, oxygen, or fluorine, which has a lone pair of electrons. Okay, so we need a nitrogen hydrogen, oxygen hydrogen, or fluorine hydrogen bond, and we need a nitrogen with a lone pair, oxygen with a lone pair, or a fluorine with a lone pair. So one of these together, one of these combinations together, will give us a hydrogen bond. So we consider this as an especially strong dipole-dipole interaction. Okay, so it is between 10 to 40 kilojoules per mole. So the strongest that we've seen so far. And the reason that this is so strong is because it's kind of like a pseudo bond. So the small, the hydrogen itself is very small, and it's almost a bare proton, right? So the electrons are being pulled away by that nitrogen, oxygen, or fluorine, leaving a bare proton there with that bond over here, right? So the nitrogen, oxygen, or fluorine is going to pull all that electron density from that hydrogen, making it basically like a bare nitrogen, or sorry, bare hydrogen. And then the electron pair from the nitrogen, oxygen, or fluorine is going to come in and make a pseudo bond, which is what we call a hydrogen bond. It looks like this. And we have the hydrogen bond donor, that's going to be the thing with the hydrogen, and the hydrogen bond acceptor, that's the thing with the electron pair. So, of course, the strength is going to vary by if it's a nitrogen, oxygen, or fluorine. Fluorine is going to have the strongest dipoles, so it's going to result in the strongest hydrogen bond. So if we have HF, for instance, that's going to be a stronger hydrogen bond between the electron pair on the fluorine and the hydrogen of another HF than we will see in water. And then our weakest would be a nitrogen hydrogen, right? And it's because our nitrogen is the least electronegative, our fluorine is the most electronegative. Okay. One last thing I want to go over in here is our strength of our intermolecular forces to kind of compare. So all of our intermolecular forces, look at real quick. We see hydrogen bondings in ice and water. We'll talk a little bit more about that, but I just wanted to bring this up. Our hydrogen bonds in ice are longer because it's had time to form a hydrogen bond. And then in liquid water, they're going to be a little bit shorter because of all the energy. And that's why we have ice being less dense than water, because of those hydrogen bonds. Okay, let's last look at our strength of intermolecular force. Looking at comparison. Okay. So if we have an intermolecular force that has, or if we're looking at our intermolecular forces, the strength is going to affect the properties we see in materials. As I said earlier, the stronger the force, the more things are held together. So if we have really strong intermolecular forces, we're going to have solids. If we have very weak intermolecular forces, we're going to have gases. Okay, so it's very important to look at these intermolecular forces because they're going to affect stuff like melting point and boiling point. We'll also look at some other things in liquids in another video. But we want to look at kind of two scenarios. If we have similar molecular weight and shape, then our dispersion forces are going to be roughly similar. Okay, so if those dispersion forces are similar, then the thing that's going to have the greatest effect on our intermolecular forces is going to be our dipole-dipole interactions, or hydrogen bonding. Okay, so molecules with greater polarity or hydrogen bonding. These are the ones that are going to have greater intermolecular forces. So they're going to be things that have higher boiling points, higher melting points, those type of things. Remembering that our hydrogen bonding, if we have hydrogen bonding, that's going to be the greatest intermolecular forces in our pure substances. If we don't have hydrogen bonding at all, but we have varying molecular weights, then our greater molecular weight is the one that's going to have our greater intermolecular force. And of course, taking into account surface area. So if we have no hydrogen bonding, but varying, or wildly varying, varying molecular weights, then our dispersion forces are going to be the most important thing. So again, greater molecular weight, greater dispersion forces, greater surface area, greater dispersion forces. Okay, just as a real quick recap, if you guys want to look at this is kind of what's going on between our three interactions. So look at that, pause if you need to, but we are done. You guys have a great day.